All right, so I think that I'm recording here. Um, they're asking us, they give us two functions, f and g, and they're asking us to determine if these functions are inverses of each other. And they're asking us to do that by finding the function composition. We want to find f composed with g and find g composed with f. If they both simplify to x, then they are inverses of each other. If they don't, then they're not. So let's come in and find f composed with g. This x squared plus 2x plus 1, I can see that it factors to x plus 1 quantity squared. So it might be to my advantage to factor that. So what does this function f do to the input? Well, f always squares it and then subtracts 1. So this time we have the fourth root of x plus 1 squared. So to try to simplify this, let's write this as rational exponents. This fourth root, I can write it instead of writing the fourth root with this radical, I can write it as an exponent of the 1/2 power. And that is the base here. What we're taking the fourth root of is x plus 1 squared. So when you have a power raised to a power, you multiply these exponents together. So 2 times 1/4 times 2, all of that is equal to 1. But remember the fourth root here. Instead, we know that the output of this has to be a positive number because of all the even exponents that we have here and even the fourth root. So to make sure that our output of this is 0 or positive, I need to put absolute value symbols around that. Now it's possible that I could later simplify, if I can show that x is always going to be bigger than or equal to -1, then I'll be able to drop those absolute values. But see, I'm not sure. So I need to find the domain of this function composition to decide whether I can simplify this to just x or not. If I can drop these absolute values, then the +1 and -1 are going to cancel. But if I don't have justification for doing that, they're going to stay there. So how do I find the domain of a function composition? Well, I think of it like an assembly line. First, I think about the input into G, and the output of G becomes the input for F. And to get a final output, we need two things to happen. This X has to be in the domain of G, and this G of X has to be in the domain of F. Otherwise, if those two things are not both true, we won't have an output. We need to find the domain of G. Well, the domain of G, we need to look at this x squared plus 2x plus 1, x squared, which we know factors to x plus 1 squared. And we can only take the fourth root of 0 or positive. We can't take the fourth root of negative numbers. So this has to be greater than or equal to 0. Well, it has a critical point of -1. And since this is equal, that's in there. And the x plus 1, hey, that's a parabola that opens upward. And that whole thing is entirely above the x-axis, and that's what we wanted. So our domain of G is all real numbers. And the domain of F is clearly all real numbers because we don't have a variable in the denominator or a radical. It's a polynomial function, it's a quadratic, and it has a domain of all real numbers. So there's absolutely no restrictions on either one of these functions. So there's no restraints on the composition of these two functions. So the domain of this is all real numbers. X can be anything. And because X can be anything, I have to make sure that X plus 1 is 0 or positive, so I cannot drop those absolute values, because if X were, say, equal to -2, then without those absolute values, we'd be saying the output is equal to -1, and that can't be true. So this can't be simplified any further, and the reason that it can't be is the domain of this function composition is all real numbers, and those absolute values are necessary. So I know that these two functions are not inverses of each other. Now, let's go ahead and find the function composition the other way and show that it's not equal to X. I suppose it could be, but I don't believe it is. All right. So what do we have here? We're trying to build the new function, the function composition, using functions f and g to get this new function g composed with f. We replace f with x squared minus 1. And this function g, what does it do? Well, it always takes a fourth root. And it takes, underneath that fourth root is always 3 terms. The first term is always the input, no matter how ugly or complicated or simple it is, and it squares it. The second term is 2 times that input, and the last term is plus 1. Well, we have an input of x squared minus 1. So we need to simplify what's underneath this radical. So x squared minus 1 quantity squared is x to the 4th minus 2x squared plus 1. And then if we distribute this 2x squared, distribute this 2 through this x squared minus 1, and here I have a bunch of things that cancel, a bunch of terms that are equal and opposite. Negative 2x squared and positive 2x squared. 1 plus 1 is 2, and 2 minus 2 is 0. So this all reduces to x to the 4th. Now, when we take an even root of this x to the 4th, we have to make sure that this x is 0 or positive. There's no way you can take the 4th root of a number and get a negative answer. So maybe I can drop these absolute value symbols. We need to think about what the domain of g composed with f is. But it doesn't take us very long to recognize that this is all real numbers, because we just got done determining that the domain of f was all real numbers, the domain of g was all real numbers. There's no restrictions placed on either one of these functions. So yeah, if x can be anything, then I can't say the 4th root of x to the 4th is equal to x, because if x were equal to some negative number, then that would not be a true statement. So I need these absolute value symbols, and since this does not reduce to just x, I know that these are not inverses of each other. All right, so I hope that helps, and I'll talk to you later. Bye.